destructive. And the reason for this is because we usually have to remove or digest or dissolve a specific amount of sample in order to do our analysis. Now, these analyses are very popular. They are routinely used in many different applications, including by IAEA, the International Atomic Energy Agency, for analysis with a very, very high level of precision and a very, very high level of sensitivity. So just as an example here, this is a typical workflow for sample receipt and analysis. So first one would receive a sample, then it would be followed by what is called NDA, non-destructive analysis, for example, using gamma screening. And then if a sample was termed as interesting, then it will be sent for sample preparation before mass spectrometry. Now, for those of you who are not familiar with mass spectrometry, this is a destructive analysis technology, is basically the gold standard when it comes to sensitivity, incredible sensitivity, precision, and accuracy when it comes, for example, to isotopic analysis, which is very important. The caveat, however, is that these types of processes take a very, very long time. So you see there are all these sample preparation steps. So these are steps before one can even do the mass spectrometry analysis. These processes can take several weeks. So although we have incredible sensitivity, this comes at a cost of time. So ideally, what we're looking for is a middle ground, right? We're looking for the best of both worlds, how we can have a very high level of sensitivity at a reasonable amount of time, and how can we transition these types of technologies outside the laboratory into the field and in remote sensing. So this is, in a sense, what our group up at Berkeley Lab really focuses on, the development of these types of technologies. And our technologies are based on ultrafast laser material interactions. Now, just as a reminder, pulse laser systems have been used in a number of applications very successfully, ranging from medicine and biology to 3D printing, thin film deposition, writing, scribing, cutting, and so on. What we are focusing on is really the world of laser-based analytical methods. So we are developing spectroscopic methods for things like isotopic analysis. We're utilizing ultra-fast phenomena, beam shaping, and emerging photon sources for developing this technology specifically for nuclear security applications. Again, we want to minimize the time that it takes to get an answer with a very high level of sensitivity and precision. So the enabling technology, the main enabling technology that we're using is called laser plasma spectrochemistry. And very briefly, what we have is a pulsed laser interacting with the material surface, leading to the formation of a plasma, which we basically take advantage of to extract information about the composition of the sample, predominantly isotopic and elemental. The way that this works, the laser interacts with the material surface, it forms a plasma. Now this plasma emits light, it's luminous, it emits photons. So by analyzing the spectral content of this plasma using an optical spectrometer, we have many different atomic and or molecular lines, and all of these are associated with the elemental or isotopic content of our sample. And we have two enabling technologies that we use. The first one focuses on elements, and it's called laser-induced breakdown spectroscopy, or LIBS, and has been around for a very long time. And then a much newer technology that was developed at Berkeley Lab that focuses on isotopic analysis, and it's called laser ablation molecular isotope spectroscopy, or LAMIS. Now, clearly, by scanning our laser beam with respect to our sample or vice versa, we can extract two-dimensional information about the composition of our sample. And more importantly, we can see what happens underneath the surface. So we can really recreate a three-dimensional representation of the isotopic composition, for example, of any given sample. And this is one of the main strengths of this technology. So just as a reminder, we are working with pulsed laser systems, which is how we're able to create these plasmas. Unlike continuous wave lasers, and continuous wave lasers are very popular, we all encounter them in our everyday lives. For example, low power laser pointer is a CW laser. So the lasers that we're using are pulsed, and we work predominantly in the femtosecond time regime. So what happens is that when we are confining a finite amount of energy in a very, very small pulse duration, you can see femtosecond is 10 to the minus 15 seconds, so a millionth of a billionth of a second. A very small pulse duration, which really leads to very high peak intensities. And this is what causes the interaction of this type of laser to form a plasma on any given sample. Other types of lasers that you may be familiar with are nanosecond lasers. They're very popular. They have a duration of 10 to the minus 9 seconds. We usually work in the following wavelength range from ultraviolet to near infrared, because this is where most commercial pulsed laser systems operate nowadays. And of course, we can play around with the energy to transition between the destructive and non-destructive regime, depending on the application of interest. Now, in terms of advantages, why these technologies, the plasma-based technologies have attracted recent interest, two main things that really make them interesting. First of all, very intuitively, they're all optical technologies. So they're based on photon excitation and photon detection. This immediately opens up the ability to potentially use them for remote sensing applications. So this is one. The second one has to do with their limit of detection. So better than part per million for LIBS, which is a fairly good number, especially considering that this is something that could potentially be used in a remote sensing sort of scenario. Now, because by shooting our laser on any material, we can basically create a sample, theoretically create a sample. This means that these technologies are not limited in terms of what type applications they can be used in. We're talking about nuclear security, but really they can be used in anything from biology to energy to environmental science, all the way to space exploration. An example that we really like to show so that people can sort of make the connection between having seen this technology before is the implementation of LIBS and the Curiosity mission in Mars. This was a mission that landed in Mars about 7 years ago or so. It was the first LIBS instrument on Mars. They were able to generate spectra within a few days after landing in what one would describe very adverse conditions. It's not the most friendly of environments. So it has been a highly successful technology for NASA. They are somewhere around 500,000 spectra in over this past 7 years. And it has been implemented in the newest mission to Mars. If you haven't been following the news over the past couple of months, the Perseverance rover has been launched to space. And it will land in Mars in early 2021. I should mention that the people responsible for the development of this sensor, the LIBS sensor on the Curiosity and the Perseverance mission, is Los Alamos National Lab in collaboration with their French counterparts. So in terms of what we do, again, we are working in the ultrafast laser regime. We are working at much faster pulse durations. And really, we're focusing on how we are exciting our sample and how we're creating a plasma. And this is very important. And the reason why it's important is that the way that we excite our plasma, especially in the ultrafast time regime, can have tremendous implications in terms of the plasma properties that we're going to form, what type of resolution we will have both in space and in time, and ultimately the spectrochemical signatures. How sensitive are we? How precise are we going to be? And as you can see here in this cartoon, the plasma properties are highly dynamic. They take place over several orders of magnitude in time scales, in terms of time scale, anywhere from the picosecond regime all the way to the microsecond or even millisecond, depending on the laser. So really mastering the sampling and really controlling these processes as much as possible can give you tremendous advantages in the analysis for nuclear security applications. So today I will briefly discuss 3 different emerging ultrafast laser approaches that we're working with. The first one has to do with the use of femtosecond filaments for remote sensing of isotopes. The second one has to do with the use of unconventional beams, such as vortex beams, to allow us to extend the distance over which we do our remote sensing. And the third one has to do with playing around with the plasma chemistry by forming weakly ionized plasma channels in order to enhance or impede specific chemical reactions in the plasma state, which we can then use to our advantage for spectroscopy purposes. So on with the first topic. I don't have to explain to this audience just how important isotopes are for many different types of applications, but importantly for nuclear security and non-proliferation. And as I mentioned earlier, the gold standard when it comes to detecting isotopes is mass spectrometry, incredible levels of sensitivity, precision, and accuracy. However, the analysis itself, as I mentioned earlier, takes a very long time, can take up to several weeks. So we're looking for things that are much, much faster than this. So the goal of this project is to develop the scientific means to measure isotopes from solids at very, very long distances, hundreds of meters or more. And really the key word here is condensed phase. So we're talking about solids. And while there have been other technologies that have been very successful in the detection of gases, things like absorption spectroscopy have been very successful in detecting isotopes in gases. In solids, there are really no mature technologies to do isotopic analysis. And the reason why these technologies did not exist is there are two main bottlenecks. There have been two main bottlenecks so far. The first one has to do with having a technology that can give us the analysis of isotopes in the solid state. And the second one has to do with the ability to remotely generate the plasma using pulsed laser systems. So back to the basics of atomic and molecular spectrometry. What we know from basic atomic spectrometry is that isotopic shifts in atoms are very, very small. Here you can see an example for boron 10 and boron 11, isotopic shift of about 2.5 picometers. Now, this is small because remember, we're trying to detect it with an optical spectrometer. Keep in mind that emission lines in laser plasmas are never as perfect as are shown here. There are always these spectral line broadening mechanisms that make the lines much, much more extended to the point where they overlap with each other, which means that we cannot resolve them. So to resolve something like this, you would have to have a very high resolution spectrometer and operate in vacuum, which of course is not something that you can do in a remote sensing scenario. Now, thankfully, if we start looking at molecular energy levels, things become a little easier. And the reason is that isotopic shifts for molecules can be actually orders of magnitude larger than they are for atoms. And in this example, you can see for boron, we can go from 2.5 picometers to 730 picometers, which means we can really see this in air with a moderate resolution spectrometer. So this is the basis of the technique LAMIS that I briefly touched upon earlier. Basically, doing our sampling in air, forcing these chemical reactions to take place in the plasma so we can form these simple diatomic oxides. They don't have to be oxides, they can be nitrides, they can be many different types of molecules. But we are creating these simple molecules and then taking advantage of the larger isotopic shifts so then we can automatically detect them with an optical spectrometer. And so far, we have been working on demonstrating this capability in different material systems. So far, you can see here a list of some of the elements and isotopes we have been able to detect. Of course, uranium, carbon-12, 13, chlorine, zirconium, strontium, and so on. So we are developing the technology to do the isotopic analysis, but at the same time, we need to remember that the second bottleneck has to do with how do we deliver enough energy on our target to create our plasma. It's not enough to just focus a laser beam. We need to have enough energy density to create a plasma. And the reason why this can be problematic is, as you may know very well, the diffraction limit. So the further away we're trying to focus a beam, the harder it is to get a small spot size. And we need to have a small spot size to create a plasma. Otherwise, this is not going to work. So with traditional nanosecond lasers, this is something that's very challenging. So we're very limited in terms of how far away we can do our focusing. But thankfully, there is a femtosecond laser phenomenon called femtosecond filamentation that allows the beams to propagate without diffraction over extended distances. And very briefly, the way that this works, it's the dynamic balance between two different phenomena. The first one is self-focusing because of the Kerr effect, meaning because we have a very high peak intensity, we have nonlinearities experienced by the beam in air. We have a change in the refractive index that causes the beam to basically focus. And then once this happens, we are forming a little spark. We are ionizing air. So this way, the beam defocuses. And this phenomenon keeps repeating itself until the filament collapses. So the takeaway point here is that the filament itself can now be a sampling source, and it has the main advantage that it can propagate for very long distances without experiencing diffraction, which is what was one of our main challenges. So here's what a femtosecond filament in our lab looks like. At the laser energies that we're working with, you would not necessarily be able to see this with the naked eye. This is long exposure photography. But you can see under long exposure, it's visually perceived as this string of white light. But again, the important point here is that the filament itself can act as a sampling source to create our ablation. And here you can see what our plasma looks like after ablation with the filament. Now, the next question that we set out to answer is just how far away can we propagate these filament beams? Of course, where we are at LBL, we're not allowed to freely shoot class 4 laser beams outside. So we had to take advantage of a limited beam path that we had in our laboratory. So what we did is basically we took the laser beam outside our lab, shot it basically in the hallway that is right outside the laser lab, which gives us a path of about 45 meters or so to get a total beam path of 200 meters. Now, the important point here is that we're bouncing the beam back and forth several times before the filament is formed. So this is what gives us the distance. If we form the filament before a mirror, then we just destroy a mirror. So it's very important to do this folding of the beam as carefully as possible. So this is what the experiments look like. So this is the entrance of our laser lab. This is a mirror. So we have our laser beam coming out of the laser lab. It's directed to this mirror, then reflected back all the way back here to the west part of the hallway, which you can see here on the right. And then, of course, we're bouncing the beam back and forth multiple times. And we also have a 20-inch telescope available to detect our signals. So at 200 meters with so I should mention that we're working with a fairly low energy system. We're somewhere around 6 millijoules, which is relatively low for what we're trying to do. We were able to ablate and create a plasma on a manganese sample. So this little spark that you see here is an actual plasma. You might see something that sort of looks like smoke. These are particles coming out of our target. And we were able to demonstrate this at this distance for manganese, zirconium, aluminum, PVC, and graphite. Now, one thing that you may notice in this video is that the beam sort of wanders a little bit. This is what defines the pointing stability of our filament. So looking at a little bit more detail about what the pointing stability of our filament is, we found, and we measured this by looking at the craters that were formed here on the outer part of this material. We found that the beam stability was about 3 millimeters, which corresponds to 10 to the minus 3 degrees at 200 meters. Now, just to give you an idea, this is actually a very positive result because this is the pointing stability that we would have if we had a regular continuous wave laser at this distance. We would always have this sort of wandering. So all in all, very promising results, again, under these control conditions in the laboratory. But of course, what we really care about is the spectroscopy. So we were able to demonstrate the ability to detect isotopes at a distance of 110 meters, which is the best distance, the longest distance that has been reported to date. And we did this using the combination of laser filaments and llamas. It's a technique that we coined as femtosecond filament llamas or F-square llamas. And of course, we can do this for many different types of isotopes. This is an example for carbon-12 and carbon-13 using samples with varying concentration of carbon-13 from 1.1 to 6.2%. But just to give you an idea of how long it takes for these measurements to be done, 30 seconds per measurement and 10 replicates per sample. So this can give you a ballpark estimate of how long it takes for us to make an assessment of the isotopic composition at a remote distance. What I showed you were the best results. What I did not show you is that there's a lot of optimization that goes behind being able to accomplish these types of distances and being able to see isotopic signature at these distances. There are many parameters that influence the filament, but the three main ones have to do with the spatial characteristics. So what are the launching optics at the exit of our laser look like? The temporal characteristics, so the pulse duration and the chirp of our laser, and of course the pulse energy. So by playing with these three parameters is how we were able to do an optimization. And looking in a little bit more detail, here we're looking at our ability to detect isotopes at a distance as a function of the convergence angle. This is the angle that is imposed exactly at the exit of the laser. We have our optics, so we are playing around with the distance between these optics, and this is what will determine how fast the beam will converge. So you can see we have very, very small differences in our convergence angle, but these small differences have a very significant effect in the intensity of the molecular bands, which is basically where the isotopic information is hidden. And of course, the temporal characteristics are also very important. Here you can see an effect of the laser pulse duration. So we are stretching or compressing our femtosecond laser pulse and playing around with the chirp and looking at the intensity of the zirconium oxide band. Again, this is where the isotopic information is contained. So you can see here by changing our pulse duration from about 200 femtoseconds to about 50 femtoseconds, we can see significant differences in the intensity of the isotopes. And similarly, by combining the spatial characteristics of the convergence angle and the pulse duration, you can see in this color map showing the intensity of the zirconium oxide band, how we can really manipulate the peak intensity of our signal in terms of maximizing the isotopic intensity. Finally, one interesting side effect that we sort of found is what is well known in the world of laser manufacturing, that if we shoot a laser and a material under specific conditions, we can form these types of structures, which are called self-organized laser-induced periodic surface structures. They have a periodicity of somewhere around hundreds of nanometers. They usually are proportional to the radiation wavelength, the laser radiation wavelength. And you can see how the morphology changes as a function of number of pulses. So this is what our sample actually looks like under a scanning electron microscope. And this is what it looks like macroscopically. Here, this is an iPhone, and we are taking images of the craters that were formed. So we're going from higher number of pulses to lower number of pulses in these three pictures. And we are looking at the macroscopic effect of the craters as a function of viewing angle. And you can see that we can resolve different types of colors depending on the angle that we're using. So what we inadvertently accomplished here was what is very well known in the field of manufacturing as structural coloration, where we can create colors on different surfaces using our lasers or other methods, and the colors are not based on pigments or dyes. They are based on the structures that are causing different diffraction effects or interference effects, which are visually perceived by the human eye. So how do we move forward? How can we get to even longer distances? By using theory and taking into account our beam expander optics, so again, the optics are at the exit of our laser, we were able to simulate what distances can be accomplished with our low energy system. and what distances could be accomplished with a much higher laser system. You can see the difference between 6 millijoules to 30 millijoules, so 50 times higher energy per pulse. So what we found is, of course, laser energy is extremely important in terms of extending our distance. One thing that we did is we have recently installed one of these systems at 300 millijoule per pulse in Los Alamos. Los Alamos is one of our collaborators on this project, and they have the ability, they have much more space than we do, and they have specific field test sites where we can freely shoot now these beams outside in the real world. This is the laser system, this is the telescope. You might be able to distinguish here where my pointer is. This is our beam path. We shoot our beam from this one window and we're detecting from the other window. So once we are able to travel again, the next step is to go out and test this very powerful laser and basically see what type of distances we can accomplish in terms of isotope detection. So we talked about technologies to do remote detection of isotopes using femtosecond lasers. And another thing that we tried was what are called sort of unconventional beam shapes. So the shape of the beam can have specific advantages or disadvantages depending on the case for the beam propagation. So as a reminder, when we have a traditional planar wave, it's characterized by its phase and the polarization, which is the direction of the oscillation of the electric field. Now, vortex beams are a newer class of beams, and they're interesting because they carry orbital angular momentum. So what is interesting about them is the phase of the beam can take many different values. And the important parameter here is this parameter F, which is called topological charge. So really what topological charge will do, it will determine how many twists any of these beams can have in a single light cycle. So I find these videos from the University of Southampton very useful just to demonstrate what is possible with these types of beams. So as a reminder, vortex beams were initially developed in order to do things like optical trapping or for free space optical telecommunications. The reason is they're very robust against atmospheric turbulence. Now, what the University of Southampton is doing here, again, working with CW lasers, they are using these vortex beams. They have these silica particles. They're using a vortex beam, and you can see they're trapping them. And then because of the orbital angular momentum, these little beads start revolving. And again, by playing around with the properties of these beams, they can they can change the orientation of the movement of the beam. And they can create what you can see here. It's called a micromill driven by light. I talked about topological charge, and the reason why this is important, it really determines how many number of twists this corkscrew type of beam will make in a single light cycle. So it can have positive or negative values depending on whether it's moving clockwise or counterclockwise. And the important point here is that these beams are quasi-non-diffracting. They're very robust against atmospheric turbulence, which makes them ideal for remote sensing applications. So what we set out to do in these experiments is, for the first time, bring these beams from the world of CW to the world of ultrafast lasers, and specifically look at the plasma spectroscopy, like I showed you with the filaments. So as a reminder, these beams have these unique wavefronts. They have differences in phase. And a direct implication of the phase singularity is that these beams will have a donut-shaped distribution. So typical Gauss beams have obviously a Gauss distribution. It would look like this in 2D. The beam intensity for the vortex beams has a distribution that's angular, much like airy beams or other types of angular beams, such as Bessel beams. Now, of course, keep in mind, these are very different because they do carry orbital angular momentum. And the effect of topological charge can be both in the beam size and the polarization states. So, for example, for the same topological charge, we can have more than one polarization. In this example, we're looking at radial and azimuthal. So in these first experiments, we took a look at optical microscope images, as you can see here. We are changing the number of pulses, topological charge 1 radial, topological charge 1 azimuthal, and topological charge 2. And what you can see is we are creating a donut-shaped imprint, as is to be expected. And for topological charge 2, we are creating a much larger crater, again, as was expected by theory. And interestingly, I talked earlier about laser-induced periodic surface structures. This is something that we can see again in these types of experiments, where these structures follow the orientation of the polarization of the vortex beam. And this is something you can probably see a little better here. This is the polarization, and you can see these different structures and how they behave. And for topological charge 2, it's sort of a mix of the two different polarizations. All of this is great, but of course what we really care about is the spectroscopy. So here we're looking at the plasma persistence. So how long does our plasma live for? Here we have an example for 3 different types of materials. We have mica, which is a dielectric, silicon, which is a semiconductor, and stainless steel. These are our test materials. And we are looking at the different types of vortex beam, topological charge 1 azimuthal, topological charge 1 radial, and topological charge 2. And and of course we're looking at, this is the wavelength, so we're analyzing this with the spectrometer, and this is the delay from the laser pulse. So all the areas that show up in black are really below the signal to background ratio. So they're considered undetectable. And what you can see are significant similarities between the same topological charge and different polarization, whereas in the case of topological charge 2, significantly reduced intensity, as was expected because of our energy density. We also looked at the plasma properties as a function of time for the different materials. We found specific trends, but they were not very clear. The important point here, though, is the range over which those fluctuated. So electron density, electron temperature, anywhere from 5,000 to 30,000 Kelvin. Electron density, anywhere from 10 to the 17th to 10 to the 18th per centimeter cube, all of which are in line with what we see with traditional femtosecond laser beams. And to us, this is a very good thing. So we find similarities in the plasma properties of these very different types of beams with beams that we know very well how to control, femtosecond beams. So in that context, this is a very positive result for us. And finally, we looked at the emission coming out of the plasma. So we're looking now at the target head-on, and these donut-shaped things that you see here, these are not the laser beam profile, this is actually the plasma profile, the plasma that's coming out of our sample. So we're looking at this as a function of time, and you can see again the usual donut-shaped beam, slightly larger for the topological charge 2, as was expected because of the energy density implications. And perhaps you can see this a little more clearly in this video. We are comparing the Gauss beam, topological charge 1 radial and topological charge 2. Again, in terms of size, slight differences, the donut-shaped beam, and we start having mixing between the different parts of the sample, anywhere around 100 to 130 nanoseconds. And this is interesting in the following context. Here we're looking at the copper emission from a topological charge 2 vortex beam. We're looking at the radial position as a function and the integrated emission intensity. So basically, we're taking the cross-section of this donut emission. And you can see we have these 2 different lobes. And importantly, this is something that can help us really understand when the mixing of the different parts of the plasma happens and how we can really use this to improve our spectroscopy capabilities, how we can use this to boost our sensitivity and boost our precision. All right, and finally, we talked about remote sensing of isotopes. We talked about new types of beams that can help us extend the distance in which we do our remote sensing. And the last point I want to touch on is the use of alternative excitation sources in the form of weakly ionized plasmas. So if we focus a femtosecond laser beam under special conditions, we can form this new excitation source. This is a weakly ionized plasma. You can see an image here. It's highly directional, and it has a size of approximately 3 or 4 millimeters. Looking at the fluorescence of the system, here you can see the N2 plus emission. The fluorescence lives for less than 10 nanoseconds. But the important point is that this can be another excitation source that we can use to our advantage. And the reason is we found that it has some interesting behavior in terms of inducing specific separations in our plasma. So we're focusing our beam, and what you're looking at here is our plasma, how it's expanding. So we're looking at it from the side. And usually you would expect it to be more like a hemisphere or something that's a little more directional in the case of a femtosecond plasma. So we're looking at this as a function of time. And what we obviously notice is this separation of the plasma that starts happening at the specific time after the laser pulse. So the plasma is actually splitting in 2 parts. Now, plasma splitting can happen under very specific conditions, but never at these types of energies that we're looking at. So it's something that probably people have seen in laser-supported detonation applications or applications in vacuum, but never for simple ablation in air by using a weakly ionized plasma channel. So we thought this was interesting, but of course this means nothing unless it has some sort of implication in terms of spectroscopy and how we can use this to detect isotopes. So here you can see our spatiotemporal contour maps. What we're looking at is the vertical distance as a function of time. So basically, you can see here we're working with the strontium titanate sample, and we're looking at the emission of titanium oxide, strontium oxide, titanium, and strontium. So basically, for the titanium oxide emission, you're able to see these 2 different lobes. The upper part corresponds to the upper part of the plasma. The lower part here corresponds to the lower part of the plasma. And you will notice that this lower lobe exists for the oxides, but it does not exist for the elements. It does not exist for titanium and strontium. So we thought this was very interesting. And then, of course, by looking at the slope of this distance to and time map, we can, of course, extrapolate information about the velocity, the expansion velocity of this upper part of the plasma. So what we found here are the velocities of the expansion of the plasma. You can see we're slightly higher than supersonic speed from hundreds of meters a second for the different elements and molecules. And on the left side, we're looking at the velocity ratio. So we're normalizing the velocity of the different elements and molecules to that of titanium. What we find in terms of theoretical is by using a very simple kinetic model where we basically assume that all the energy goes into kinetic energy, we find a pretty good, not perfect, but fairly good correlation between the observed and theoretical. Now, what this means, in other words, is that we found a correlation between the atomic mass or molecular mass and how fast these atoms and molecules travel. So basically, the lower masses will move faster, larger masses will move much slower. So this means that we have accomplished some sort of localization in where we have our oxides. And remember, we want to control where our oxides are because this is what contains the isotopic information. So we tested this with different material systems. Here you can see an example for zirconium. This was reproducible. And then the other thing that we did was do something very simple, correlate traditional femtosecond laser focusing in the focal plane versus that of having our weakly ionized plasma. So as you can see with the traditional femtosecond laser ablation, we just have plume expansion as was to be expected. In the case of the weakly ionized plasma, in this case for the titanium plasma, again, a separation. And importantly, again, very similar to the previous contour plots that we saw, the main point here, significant enhancement in the presence of oxides versus atomic species, several times or more. And again, we want to boost how many oxides we have in our plasma, because this means we're going to have better isotopic sensitivity and precision. So in conclusion, we talked about different femtosecond laser sampling approaches for isotopic analysis. We talked about the use of femtosecond laser filaments for establishing remote isotopic sensing. We also talked about the use of unconventional beams such as vortex beams to expand the distance in which we can shoot our laser beams. And we talked about the ability to tailor our chemical reactions to specifically enhance or impede reactions in order to boost our sensitivity. So I think I'm running out of time, so I'm just gonna go through these other slides. I just want to acknowledge my incredible group at LBL who have contributed to this work. Here you can see them in action. And with that, I will thank you. If you're interested in learning more about what we do or interested in working with us, please feel free to send me an email. And I'll be happy to answer any questions you may have.
Thank you so much. And as a reminder to everyone who's tuned in, I'm about to repost the link to ask questions in the chat box. But we already have a few questions, so I'll go ahead and read them from our participants.
Sure.
The first question is, how do you ensure that the filament is formed after the final mirror instead of prematurely in between mirrors?
Yeah.
Also, if the generation point of the filament can be controlled, isn't the more important distance to notate the total filament distance rather than the total laser distance?
Yeah. So these are great questions. So yes, so the filament itself has a finite distance, and the propagation distance is something completely different, right? So these are two completely different concepts. To answer the first question, the reason why I mentioned there's a lot of optimization that goes into this, especially when we're working with mirrors, is to avoid burning some of them. And we have burned quite a few of them until we got things right. So I mentioned these are the three main buttons that we play around with: the spatial characteristics, the temporal characteristics, and pulse energy. And this is how we determine exactly where the filament forms and for how long it propagates. So both the filament propagation, the laser propagation without the filament, and then the filament propagation itself. What was the second question? Please remind me.
Sure. It says, the second question, also, if the generation point of the filament can be controlled, isn't the more important distance to notate the total filament distance rather than the total laser distance?
Yes, absolutely. So in our case, keep in mind that when we're doing the 200 meters experiments, we were limited in how long the filament distance is, right? Because we only had from this last mirror, which we were hoping not to burn, to where our target was, which was less than 45 meters. So to answer your question, both of them are extremely important. We want to have great control of where your filament forms and for how long it propagates. That said, keep in mind that having all these mirrors, this is something that we did only because we did not have the beam path available to shoot our beam. Things are much easier when you're shooting the beam directly outside, right? So you don't have to worry about the mirrors. You have full control of where your filament can form and for how long it propagates. So this lifts the limitations. That said, you have to start worrying about other things: atmospheric turbulence, dust, and things like that that can slightly tweak where you have your self-focusing and where your filament will form.
Okay, great. Another question from Kathy Shield. What's the minimum quantity of an isotope you can identify or differentiate from another isotope?
Yeah, very good question. So, so far we have demonstrated, so I guess the best way to put it is in terms of precision. So precision in determining the isotopic ratios. We have been able to do about 0.2% precision. And just to give you a comparison, compared to TIMS, thermal ionization mass spectrometry, which is really the gold standard, we are about more than one order of magnitude below what they can do. One order of magnitude below where TIMS is, but keep in mind that thermal ionization mass spectrometry, as I mentioned earlier, requires several weeks for sample preparation, purification before you can do the measurement. And of course, this is a measurement that takes a few seconds to a few minutes, and also opens up the ability to do things in remote distances, which is of course not something you can do with a mass spectrometer. Obviously it's not exactly, we cannot really compare, right? And this is the best results that we got, but you can see the direction in which we're going.
Thank you for that answer. Is there any other questions from the audience?
I had a question about the spot size for the laser ablation method for the isotope detection.
You mean in general, or in the context of filaments, or both?
Well, both, and then also, what is the resolution of the measurement? So, like, if you had a sample that was like mixed isotopes, and you wanted to know, like, spatially how they were distributed or something like that, what is the spatial resolution you have?
Very good question. So, doing direct ablation, let's say in the lab, where with the femtosecond laser, where you have very good control of what you're doing. The record that we have in our lab, and the record when it comes to the ability to do ablation, is 450 nanometers. Now, this is for cases where you want to do very high resolution mapping, for example, right? And this is in model systems. It's not going to be as great in every single system. Now, the reason why we have not been able to go lower than 450 nanometers is because of the diffraction limit again. But this is in a different sort of aspect, right? So the diffraction limit basically tells us that we can focus photons in dimensions much lower than half the radiation wavelength. So given the fact that we're operating anywhere from, let's say, 200 nanometers to 1 micron, roughly, you can understand that we can't really focus our beam much more than that if we're doing traditional ablation. In the case of filaments, things are a little different. So the filament is usually a little larger diameter, at least the filaments that we have been working with. So it can be of the order of hundreds of microns. We have not systematically tried to reduce this because this has not been our focus. I understand from your question you're interested in spatially resolved isotopic analysis. So for the filament, we're somewhere around in the hundreds of microns, but I'm sure we can get much better if we look systematically into improving this type of resolution.
So have you? Thanks for the answer. That was sort of more than what I asked, but. Have you looked at so in many, I guess, biological techniques, they do a technique called like super resolution spectroscopy, where they overcome the diffraction limit by doing like stochastic images at different timestamps and then reconstructing. So have you guys tried doing any of that to overcome the 450 nanometer resolution with I guess without the filaments?
Yeah. So that's an excellent question. So we have done different work that I didn't talk about here, but it's a slightly different approach. So I believe what you're talking about is mostly applies to sort of fluorescence and so on. What we have done is we have used near field optics to beat the diffraction limit. So basically, coupling our laser beam to an atomic force microscope tip or a near-field scanning optical microscope tip. And this gives us the ability to go well beyond the diffraction limit. So we were able to go to 27 nanometers in the optical near field. However,
okay, wow, that is super cool.
Yeah, but keep in mind just how hard it is to operate an instrument like that, right? So this is strictly a laboratory application and very, very hard to operate.
Got it. And I guess even like the optical alignment is extremely sensitive and such. I see.
Yes.
Super. Okay, that's just super awesome. Thank you so much.
Sure.
Is there any other questions? All right, well, we're just about at time now, so you can join me in thanking Dr. Zorba for presenting today. Thank you so much.
Great. Thanks, everyone.
Thank you.